So I'll quickly wanted to introduce our next speaker. We have Bhavesh Bhatt here. So Bhavesh Bhatt is a senior data scientist based out of Mumbai. His primary interests are computer vision, machine learning, deep learning. He's also designed and deployed many machine learning and deep learning models and have made significant business impacts. So Bhavesh is also a Google developer expert since 2019, and he has contributed a lot to the Google developer community ecosystem and in general. He also has a YouTube channel. He has wonderful content posted in his YouTube channel. Please check those out. And he's also awarded as a 40 under 40 data scientist by Analytics India magazine in Jan 2020. So Bhavesh, thanks for accepting the invite and sharing your knowledge in this Kalambagam event. And before Bhavesh session, I would also like to thank Prasad and Google for Developers. And I wanted to ask Prasad to share few words now. Prasad, over
Yeah,
to you.
sure. Thank you so much, Navneet. And thank you so much, Abhinandan. I really liked your talk. It was very much inspiring as well as insightful on what's happening with LLM, specifically with the Tamil language. And the next step that you shared will be very useful for all the developers right now attending the event to build their own LLM for the Tamil language. And yeah, so I'll just give a short intro about myself. I'm Prasad Seth. I'm a community manager at Google, and I lead a couple of community programs, specifically TensorFlow user groups in more than 30 cities of India. Apart from that, I also manage Indie Games Group, which is a community of professional game developers. It's supported by Google Play. And another program that I manage is basically collaboration and partnerships with various communities across India, similar to what we are having right now. So we have collaborated with AI Tamil Nadu for this event, uh, Kalambagam, and yeah, today we have GD Bhavesh Bhatt. He'll be delivering an insightful talk about how to talk to Neo 4J database in a natural language using Google's Gemini model. And yeah, once again, thank you so much, AI Tamil Nadu, for organizing such a wonderful event for developers. And yeah, without much ado, I would request Bhavesh to take over.
Awesome, cool. Thank you so much, Prasad, for the introduction, and thank you, Navneet, for the introduction. I'll quickly start today's session by presenting my slides, and then I'll also hopefully give you like a flavor of how you can use large language models for your use cases. So I'll quickly share my screen. Can all of you see my screen?
Yes, Bhavesh.
Perfect. So we've already discussed about the topic that we'll be discussing today, that how do you talk to a Neo4j database in natural language using Google's Gemini model. So I'll quickly start by, so again, the introductions are already done, so I'll quickly skip this and we'll quickly move forward. So I'll start with what a large language model is. So when you think of a large language model, be it say Llama 2 or be it the Gemma model that's recently released, all of the large language models are basically advanced machine learning models that have been designed to understand and generate human-like text. These models are basically built upon deep learning techniques and neural networks that process vast amounts of data to learn grammar, syntax, context, and semantics. What sets a large language model apart is, again, if you look at or if you go by the name of a large language model, the reason why it's large is because the overall structure of the entire LLM is huge in terms of the total number of trainable parameters it has. Secondly, the reason why it's called large again is because of the amount of data that it has been trained on. So imagine if you have like a model that has been trained on a good say 70-80% chunk of the internet, which is where it kind of derives its name from, say the large training corpus as well as the large say weight matrix that it has. So that is where an LLM comes into picture. Just to put across what an LLM does behind the hood, again, there are multiple modifications of how a large language model works. But the idea is most of the large language models are next word predictors. And when you think about a next word predictors, the core idea is how can it predict the next word with higher, say, probability with respect to creating a coherent sentence is where say a next word predictor comes in. So if I input a sentence like cat sat on a, and if I pass it through a large language model, which is like a series of a neural network which has weights in which has basically multiple weights, then the output that would come out will be mat. So all the large language models that generate output will be one at a time, and it wouldn't give out the entire response that you're expecting for in one go. Okay, so I'll cover the different aspects of how LLMs are used currently. So large language models can be fine-tuned for a classification task. An LLM can also be used for searching what you're say searching for. You can summarize documents. You can basically rewrite the entire sentence. You can generate new sentences, or you can generate new paragraphs, or basically generate new text. You can cluster text into multiple clusters that are present, and then you can extract useful information out of what you are aiming to extract out of the entire text corpus that you have. So there are various use cases of how a large language model can be used today. Say, for example, let me start off with a simple example. If you input, say, a simple sentence, like a part of a sentence into a large language model, like roses are red, the output will be given out as something like this: violets are blue, sugar is sweet. So here, if you see the output that's generated, the output is, or the output will be one word at a time. So when I input roses are red, the large language model will output violets first, then it will output are, then it will output blue, then it will output sugar, then is, and then sweet. So it will kind of output one word at a time so that you are able to create the entire sentence. Now the output that is generated at, say, an X timestamp will be again fed back as an input along with the overall text that has been used to create that output, and then the new output will be generated. So here your output is one word at a time, which is something that you might have seen while all the LLMs produce output as well. Similarly, if you have some piece of code like this, like for variable I equal to 0, and if you pass this to a large language model, this is a sample text that it will produce, which is it will try to understand what the next piece of text or token would be in terms of the output, take that output as an input, and then again produce an output till the time you kind of have your entire output ready. So in short, this is how a large language model functions. I'm unable to see if there are chat messages coming in. We can have like a small Q&A at the end if we get time. So I'm unable to see the questions right now, but yeah, I'll quickly move forward. So here, one uniqueness about a large language model is if you want, like, if you give it a simple question like give me 5 neat project ideas for science fair projects, then the output will also show you or give you output such as build a volcano, build a 3D printer, and so on and so forth. So today's day and age, what we are seeing is there are multiple use cases of how LLMs are being used. A lot of times we are kind of optimizing content based on the content that already exists on social media platforms or on e-commerce websites. So there's a lot of research that's happening on LLM because there's a wide usage of how LLMs can be used, like the customer facing industry or the other IT sectors where there is good amount of, say, humans involved. How can we automate that process to make their life easy is where LLMs are playing a crucial role. Now, the basic idea is why LLMs are gaining popularity is you cannot train as a user, as an end user, even if you have like good enough access to a GPU, like a decent sized GPU or a GPU sized cluster as well, you cannot build a large language model from scratch, right? From the initial model to the final product, which is trained on good amount of internet data, which is where what you can do at best is take an already existing model and then fine tune it for your use cases. So the idea is you have to think of how you can say take a large language model and how you can use it to prototype quickly is where say LLMs come into picture. All of the LLMs that we are seeing right now, which say are gaining so much of popularity, the core has been the transformer model. Transformers was first outlined in a 2017 paper published by Google called Attention is All You Need, which utilizes a self-attention mechanism to solve sequence-to-sequence tasks. So the initial attention is all you need model was based on the fundamental idea of converting language, so converting text in one language to the other. It basically had two major chunks. So the chunk that you see here is the encoder. The chunk that you see here is a decoder. You feed in the inputs here. So all your inputs get converted into an embedding. The embedding passes through a multi-head attention block. Now, the idea of multi-head attention is, given if you have a sentence with 20 words, how do you assess that which word is dependent or which word relies on the other words, which is something, if you want to understand, is where multi-head attention comes in. You pass all of that data into add a normalization layer. Then you have a feed forward layer, and essentially the output of an encoder block in the attention network is a more context aware embedding as compared to the vanilla embeddings that enter here. Okay. Now these embeddings are passed again through the query and key matrices, and they pass through the decoder inputs as well. So here, if you have to generate text, you will have a start of output token that is fed in here. You have your modified or your custom embeddings that are generated that come in here, and then you have the final output generated again. So the bare bone or the skeleton of most of the large language model today are based on the transformer networks. Again, there's good amount of research going on in terms of how we can optimize the transformer network as well. But still, most of the models that you see today or most of the LLMs that you see today are a result of this basic architecture called the transformer network. Now, there are different LLMs that we've already heard of. So the GPTs of the world are a decoder only model. So what I showed you here was an encoder and decoder only model. So you had an encoder stack and you have a decoder stack. When you consider, say, BERT, BERT is an encoder only model. So if you have a simple, say, classification task that you have in mind, what you can do is you have a CLS token that is outputted out of an encoder block. You can take the CLS token, apply same amount of classification there, and then use this as a classification. So you can fine tune BERT for your classification task as well. Decoder only models keep generating text. So the GPTs of the world, like GPT-2, GPT-3, and the other GPT series models will kind of generate text for you based on the inputs that you provide. And then if you have language translation task, you will have a combination of an encoder and a decoder. Okay. Now, with this idea, we are fairly placed in terms of how a large language model works. Now, we'll go to something called as what a graph is. So basically, I've divided this section or this entire talk into 3 chunks of 10-minute talks, where the first chunk is talking about large language models. The second chunk, which I'll cover currently, is I'll give you an idea in terms of graphs. And the final chunk is where I'll kind of take you through how you can use Google's Gemini model in terms of creating a smart prompt and then utilizing it for your use case. In our case, the use case is how do we talk to a graph database in natural language. Okay. So simply put, a graph is a set of discrete entities, each of which has some set of relationships with other entities. If I show you a simple graph, one of the major graph that you are able to utilize right now as well is the internet. So if you're connected to this particular call on Google Meet, essentially what you are witnessing is a connection that is established between you and the server where this entire session is live. So think of every node in the internet as a graph. Think of your simple H2O molecule as a graph as well, where you have an oxygen molecule and you have 2 hydrogen molecules as well. Even this can be represented as a graph. Now, why am I speaking about graphs and not any other databases? Well, initially, the entire journey of collection of data started with relational databases, which was structured, and it was fairly good for the amount of data that we were able to generate in 1980s. But as we kept moving forward, we realized that scaling a relational database is not so easy, which is where NoSQL databases came in after 2005, where you have multiple ways of, say, optimizing the overall databases. So relational database, say NoSQL databases could scale really well. Then came from 2013 onwards, we have graph databases. Now, the uniqueness of graph databases and why it's gaining so much of popularity is not only is it flexible in terms of storage, but your retrieval is also very quick. One unique thing that differentiates a graph database from a NoSQL database is it's able to capture relationships really well. Now, in a NoSQL database, we have good amount of throughput that comes out because of how it's designed. But one of the places where it's not able to really give us the output that we desire is are the places where there are relationships inherently involved in a data set. So that is where a NoSQL database struggles. Relational databases are good at storing relations, but it doesn't scale really well, which is where you have a combination of a graph database that comes in, which kind of rectifies the problems that we face with relational databases and NoSQL databases. I'll quickly take you through some basic building blocks of how you define a graph. So a graph contains nodes or vertices. Nodes are say useful in form of storing, say, data in form of properties. How do you differentiate, or how do you understand whether a piece of a network can be combined into a graph or a node? When you ask a question, like if I ask a question to a database, say for example, which actors play in the movie, or how many movies did the director direct? Whatever nouns that you can think of, all of those nouns are basically part of your nodes that exist. Going forward, there are relationships that are captured between nodes. So all of these relationships are not bidirectional but unidirectional. So if you consider a relationship as well, and if you have to find out a relationship in a graph, then ideally all the verbs in your graph, all the verbs in your questions or in your statements with respect to the data set that you're considering, all of these will basically be your say relationships that are connecting two nodes. Say for example, if I have like a node of MacBook, then there are nodes that can be identified using labels. And then you also have properties, which are specific key value pairs. The reason why this becomes so important or exclusive is because while searching, if you are only looking at or if you want to filter out nodes based on some key value pairs, then you can automatically do that using the properties that exist for a node. Similarly, if there is now you might have a question like, how do you convert your existing relational databases to a graph database? If I ever want to make that jump, and if I see a lot of merit in terms of creating or converting a graph, say a relational database into a graph database, how do I do that? So the rows would be converted to individual nodes. Your joins, if you have multiple tables in a MySQL database, if I want to convert that into a graph, then there are multiple joins that are there. Your table names would become labels, and your columns, individual columns, would become properties. So this is like a mapping that helps you understand how you can convert a MySQL database to a graph database. Okay. Now, for a MySQL database, you have SQL, which is structured query language in terms of, say, getting or fetching the data. But in case of a graph database, the language that is used is something called as Cypher. So what you see here is two nodes. So you have a customer node and you have a product node, and then you have a relationship like rated. Now, if I have to reference these set of nodes, now you can have multiple such nodes with the same set of properties as well, but with different names. Now, how do you reference or how do you find out nodes which fall into this particular condition? Well, the idea is you have round brackets to say access the nodes that you're looking for or searching for. So here what I do is I say double dot customer double dot product. I define the direction of the relationship. So the customer will rate a product, which is where the relationship goes from customer node to a product node. And then I also define the relationship which is rated. in order to better write cipher queries, what I'll do is I'll give them a short form or a short notation which I can access while creating the query. Now, if I want to find out all the customers, if I want to find out all the customers who have rated a particular product and I want to return different things out of the query that is generated, like the customer name, the product name, and the stars that have been given by that particular customer for that particular product, then this is a sample cipher query. Again, once you kind of start using Neo4j, you will get a hang of how things are, but this is the bare minimum idea that you require in order to move forward. So this is something that I wanted to show you with respect to graph databases as well. In Neo4j, this is how the overall select star from table looks like. So the command is match and return n. Here you see a graph database with multiple types of nodes. So you have movie nodes and you have person node, and there are different relationships. So I'm basically looking at a database which contains people and movies. For different movies, there are different people who have contributed in a different aspect. Like a person can be a director, a person can be a producer, a person would be a writer for a movie. All of these relationships are captured into this particular graph database. Okay, so if I'm assuming everyone's seen the Matrix. So if you look at the Matrix, the movie, like the Matrix Reloaded, the Matrix, the original Matrix as well, all of these relationships are signifying what that particular person has contributed to. Okay, so Joel Silver has basically produced the movie, which is what is evident in these relationships that you see here. Similarly, for the Matrix Reloaded, again, what I wanted to also show you is every node has a property like the ID, the released year, the tagline, and the title of the movie. Okay. Similarly, you have node properties like this, like for example, for every person you have a year of birth as well as the name of that particular person. Now I'll kind of switch our focus to how you can kind of ask questions to your graph databases. So this is the third part of the demo that I wanted to show you. So this is the screen of Google AI Studio. Currently, you have access to say Gemini Pro 1.0 as well as some initial testers also have access to Gemini Pro 1.5, which is multimodal in nature. Given everyone can access Gemini Pro 1 through their simple Google accounts without paying anything, you just require an API key to utilize this. What I'll show you right now is the prompt that I've used to smartly convert my natural language questions into cipher queries. Okay. So this is the initial part of the prompt, which is you are an expert in converting English questions to a Neo4j cipher graph code. The graph has the following node labels. So with every graph that you create, okay, what you can do is you can smartly share the prompt. So what I'm doing here in this piece of code is supplying the schema of how my database looks like. So I'm defining what my nodes are, I'm defining what my relationships are, and I'm also defining how my relationship directions are. So here, if you look at things very carefully, all the relationships start from the person node and go till the end movie node. There is no reverse direction of the nodes that are there in terms of how the relationships are defined. So I also give few short examples. So for a lot of use cases, what you should also do is you can also if while defining the prompt, what you also can do is you can give some few short examples in order to teach the large language model what you are expecting in terms of inputs and outputs. So what I've done here is I've given some few short examples. Like if I ask a simple question, list down 5 movies that released after the year 2000, the cipher command will be something like this. Okay. Similarly, I've given the second example, the third example, and I don't want this set of output to appear, which is where I also have this as a prompt. I have this as part of the prompt itself. Okay. Now everything's done. What I do is I pass this through the Google AI Studio prompt editor, and I test out a prompt. And if I ask now, say if I pass in the input, name the director of the movie, The Matrix Reloaded, this is the output that I get. Now, for Gemini Gemini Pro 1.0, there is a possibility of you exporting this entire piece of prompt along with what you want to achieve in form of a Python template. There are other templates as well. So what I do is essentially I create the entire prompt into a Python function, which is what is encoded here. Then what I do is this particular function, whatever cipher code is generated, I take that cipher code, I create a session in Neo4j. So there are drivers that are available where you can connect to say a Neo4j graph database using Python, which is what I'm doing here. This is how you kind of connect. So this is the connection code that helps you establish your connection with the Neo4j graph database. And I'm using a simple library by Hugging Face called as Gradio for creating an interface where you can pass in an input sentence in form of text and then get an output in form of say the cipher query that is generated internally by these set of functions, and all that cipher query that is generated will run automatically into Neo4j. The output will be given back to you, and then you can say basically enjoy having like a conversational agent with your Neo4j graph database. Okay. Now, rather than showing you slides, I'll show you how this looks as well in totality. So let me know if you can see my screen. I'm assuming everyone would be able to see the screen as well. So I'll ask a simple question. This is still running on Google Colab. So who directed the movie The Matrix? So if this is the question that I ask, then behind the scene, what it's happening is it's firstly creating from this particular piece of say language. It's basically creating a cipher query. The cipher query is then executing on the Neo4j database, and then the results are what is populated in this particular dashboard. Again, this is like a live say web page that I'm accessing, so nothing's predefined here. Then if I ask a simple question, name the actors of the movie The Matrix, then there are different other movies as well, which is part of this particular database. So if I ask the same set of questions again, so these were the actors in the movie The Matrix. Then there is one more movie, I believe, Harry Met Sally is also When Harry Met Sally. If you goof up the code here and there, it might give you an error, but let's see if it works currently for us. So yeah, I mean, here is where you see the output as well, right? So imagine the kind of use cases that you can solve using the Gemini model that's available. So if you want to create like an entire fine-tuned version of your MySQL database or a Neo4j database or any database that you have, you can use Gemma, which is the open source model that has been recently released. If you are not very comfortable, or if you don't have the resources in terms of the fine tuning aspect of how you can fine tune a model at your end, then what you can do is, if you don't have like a very complex database to play around with, then what you can essentially do is you can basically take the entire piece of data that you have and create a good smart prompt, and you can start utilizing the Gemini Pro models that are there. So based on how you and your organization is placed currently in terms of creating custom LLM solutions, there are different offerings that are part of what you can use. All of these are like say given by Google right now. One is the Gemma model, which is something that you can download and fine tune. If you have the right set of resources, you can fine tune Gemma for your use cases. The other piece is, if at all, if you don't have that heavy an infrastructure at your end, what you can do is, for simpler use cases, you can create a smart prompt and then utilize the Gemini Pro model that already is say given to all of you to try out as well. So yeah, I mean, this is all that I had in today's session. Yeah, I mean, I hope all of you enjoyed the session, and I'll quickly check the questions. Okay, the WhatsApp group, right? Okay, cool. So perfect. This is all that I had in today's session. I hope you found this informative and interesting. This was something that I wanted to share across with all of you today.
Yeah, thanks, Bhavesh. That was a wonderful session. And connecting LLMs or creating chatbots on top of databases are one of the most common use cases that everyone would love to try. And collab implementation on collab with Gemini Pro as the backend and then Neo4j database. It was really insightful. And the questions are posted in the Q&A section. I would like to ask one question
Yeah.
I would like to read it. What is the difference between using Neo4j versus something like Pinecone plus RAG? Or both just variations or same thing?
So Pinecone plus RAG falls into the category of a vector database. So imagine a use case where you have like a huge PDF, right? So when you have a huge PDF and if you want to ask questions on that PDF is where vector databases come into picture. So when you think of a vector database, that is different as compared to a graph database. Now think of a graph database as your MySQL database, where your MySQL database is converted into a faster version using a Neo4j graph database. So if you have, if you want to quickly query and get results out of a Neo4j database, and again, the data that I've used right now in this particular example is very short, but if you imagine, if you have like 1 million rows of structured data, and if you want to create queries and get results in say less than a second, which is where you can utilize a graph database like Neo4j. Vector databases are totally different. Vector databases fall into the category of, if you have to retrieve results to get better LLM responses, then you use RAGs along with vector databases. So this is how I would put it across. So both of them are totally different. Yeah.
Okay.
Yeah.
Thanks, Bhavesh. Due to time constraint, we are moving to the next session. Thanks, Bhavesh, for delivering this talk. Would love to host you for more events in the future. Thank you.
Thank you so much. Thank you.